Good evening. Questions you want to ask before we get started? I haven't got too many questions. All right, well, tonight we want to get some different coordinate systems that you'll use again in Calculus 4. We mentioned cylindrical coordinates. If you don't like the pictures you see here and you don't like the ones you see in the book, there are actually lots of sites that have good pictures of these. If you go out to one of the things like Wikipedia, Google Wikipedia cylindrical coordinates or Wikipedia spherical coordinates, it'll give you a nice write-up on these that's short and to the point. Or you go to some of these other things like Paul's Online Math Notes or Purple Math or one of those other popular math sites. Math Inside, I think, has some. We're called cylindrical coordinates. All we did was we added z to polar coordinates. So you can take any point, drop a perpendicular down to the xy plane. We call this distance out from the origin r, this angle within the xy plane theta, and this height up here z, right? And we can identify a point by its r, theta, z coordinates. And we said it's just polar coordinates at z, except that we don't allow r to be negative anymore. So r is always the square root of x squared plus y squared. Theta is the same as it was in polar coordinates. It's just tangent theta equals y over x, therefore, with theta now pointing into the right quadrant r, since we don't allow r to be negative. So theta in the quadrant of xy. So it might be the arc tangent, or it might be the arc tangent plus pi. If you're ever in doubt, I didn't get a chance to talk to you too much about it last time, but in fact, let me put the last coordinate here, z equals z. In fact, there is a function that will compute this for you, because this comes up all the time. What you have here is that theta, when it's pointing into the correct quadrant, is going to be equal to the arc tangent of y over x. If it points into the same quadrant as x, y. Well, the arc tangent always points into quadrant 1 or 4, right? The arc tangent is the unique angle between, imagining this as I go along my finger, between plus and minus pi over 2, right? It's, maybe this is the arc tangent. But between here and here, so if your point is in quadrants 1 or 4, anyway, I said 1 or 2 before, didn't I? In quadrants 1 or 4, then you want to use the arc tangent. So generally what we do in this class is we figure it exactly on the unit circle, but if it's not an exact angle, if it's not a special angle, then you can use the arc tangent function provided you're in quadrants 1 or 4. However, if you're in quadrants 2 or 3, then you want to use this angle here. So this would be theta equals arc tangent y over x. And this one over here is going to be arc tangent plus pi always. So if the point you're looking at is in quadrants 1 or 4, use the arc tangent, but if it's over here or here, quadrants 2 or 3, we'll use arc tangent plus pi. Or 180 degrees if you're in degrees. Now, there's always a chance that it's along the y-axis somewhere, in which case x is 0 and you can't do this computation at all. So if x equals 0, y is positive, you put, oops, wrong spot. X is 0, y is positive, then you say that the angle, well, I was pointing along the positive z-axis, so theta equals pi over 2. If x is 0 and y is negative, you're down the negative y-axis and you're looking at 3 pi over 2. Or you can call it minus pi over 2, whichever way you want. And so it's complicated. We put these in parentheses. Furthermore, maybe you want the angle to always be between minus pi and pi. That's actually a common convention. It's used in a lot of applications. If you want it to be between plus or minus 180 degrees, then you have to modify this further and say, well, it's arctangent plus pi if you're in quadrant 4. But it's arctangent y over x minus pi. You go to the angle here and drop pi if you want to be in quadrant 3. Well, that's what your mind kind of has to figure out as you go along. And like I say, this comes up so often that there is a programming function. This setup where it calculates the unique angle between plus and minus pi and then I have to put this one also if y equals 0 and x is less than 0, then it puts the angle pi. And it puts the angle 0. That's getting complicated now. Technically, if you're along the x-axis, that's not in any quadrant, that's a quadrantal angle. So if you get the angle 0, if x is greater than 0, y equals 0. Well, it breaks it up in all these cases if you want to make sure it's between minus pi and pi. This computes it and is programmed in many programming languages as a tan 2. So theta equals a tan 2 of the y coordinate first and then x, a tan 2 y x, in programming language such as MATLAB or C++ has had this available, and other languages also. I think Fortran, if you use that, has a tan 2 available. So, and if you use the MATLAB equivalent, Octave, lots of other languages. These aren't always. This isn't always available on the calculator. I think depends on the calculator. But if you're doing a programming language, you can avoid this quandary of almost different cases by just calling a tan 2 of y over x. The one case that fails is if x and y are both 0. You notice that's not in here because there's no angle, right? And this thing will also give you a domain error if you put both x and y equal to 0. But we'll say that. Now we wanted to do some examples. We didn't get very many examples last time. We can do a couple more. Convert the following. Minus 4, 4, minus 7 to cylindrical coordinates. Suppose those are rectangular coordinates. What do I do? Well, I think of these as polar coordinates. And I say r equals square root x squared plus y squared. Gives me, let's see, square root of 32 is 4 square root 2 r. Then I say tangent theta, this is the hard one, is y over x is 4 over minus 4. Negative 1. And then I have to figure that out on the unit circle exactly where it is, right? If the arctangent is negative 1, I can think of that as minus square root 2 over 2 over plus square root 2 over 2. That would be a the ratio -1, and this would then be the y and x on the unit circle. That corresponds to that, so I'd go to y equals minus square root 2 over 2. X equals plus square root 2 over 2 back here. So this point right here, and the other thing that could happen is this might be the ratio of square root 2 over 2 over minus square root 2 over 2 would also give a point where the tangent was -1, y was minus x in this direction. So you get the two opposite angles always have the same tangents. And this one goes out to x equals minus square root 2 over 2 and y equals square root 2 over 2. And which angle is it? You have to go in the same quadrant as this one. And this one, x was negative and y is positive, so we want this angle for theta to go into the proper quadrant. So apparently it's the angle, well, this is a square root 2 over 2, square root 2 over 2, one triangle. This angle must be a pi over 4 angle, so we take pi back up pi over 4. Did one like this last time and say the angle here is 3 pi over 4. Right, so, but you can look at it and see, right? Once you see these two are equal, you know it's pi over 4 angle. And then z is equal to c is -7, and so the coordinates are r4 square root 2, theta 3 pi over 4, z -7. There's the cylindrical coordinates, but these rectangular coordinates. It's not too bad. But again, if this is not a special angle, so you can't find this angle exactly in the unit circle, then use this a tan2 function or use your calculator. And as far as I'm concerned, you don't have to put the angle between minus pi and pi, put that in for your education. What you can do is just a simple case. If it's in quadrants 1 or 4, you take the arctangent. If it's in quadrants 2 or 3, you take arctangent plus pi. And then if it's on an axis, it's obvious, right? Simple by hand. Theta equals arctangent pi over x. Then quadrant 1 or quadrant 4. Theta equals arctangent y over x. So by hand, not requiring for all the special cases. Minus pi over 2 less than x less than or equal to 2. You take this plus pi in quadrants 2 or 3. Then you say it's just obvious on an axis. There you go. That's what we can do for those. All right, so that's a reminder of cylindrical coordinates. Now we also want to do one more that's very useful, spherical coordinates. Spherical coordinates work like this. I've got a picture on the computer. Let me try and run it up here. There are lots of problems where there's a radial symmetry from the origin in all directions in 3 space. So you consider a point like this, an arbitrary point you can think of like you do with cylindrical coordinates, dropping a perpendicular down to the xy plane, running this line segment out on the xy plane. So this is a right angle here. So you drop the perpendicular. And calling this angle theta as before the angle in the xy plane. So we'll carry theta in spherical coordinates as well as in cylindrical coordinates. But now I'm going to, instead of taking the line segment here, I'm going to take the line segment out to the point itself, and I'm going to call that length rho. So rho will be the distance from the origin to this point. And if you think about it for a minute, you can figure it. This distance here right? From cylindrical coordinates is square root x squared plus y squared, right? This one here is z. So what is rho? Well, this is a right triangle here. So rho is the square root of this squared plus this squared, right? Rho equals square root of this side of the triangle, z squared, plus this side of the triangle squared, square root x squared plus y squared. Squared. Oh, but that's just square root of x squared plus y squared from that one, plus z squared from this one. And so the distance to any point in Euclidean space, the origin is rho equal x squared plus y squared plus z squared square root. There it is. That'll be one coordinate. We'll also keep theta from cylindrical coordinates, and then we're going to add this other coordinate, the angle down from the positive z-axis. We'll call that phi. And now we can identify a unique point by picking rho, theta, and phi. That will be called spherical coordinates. And you put them in that order, rho first, then theta, then phi. These don't look like the letters on the Greek houses. That's because these are the small letters, right? And on those you'd see a capital phi and a bigger, bolder theta, maybe something like that or something. Say again?
It's rho, theta, what's the one on the
Oh,
end?
phi.
Phi.
Yeah. Yeah. Now, what we've found is these conversions, if we're given rectangular coordinates x, y, z, call these equations 1 to 9, we deduced from the Pythagorean theorem here for this right triangle that rho square root x squared plus y squared plus z squared. It's never negative. It's the same theta as before, so once again, tangent theta is y over x, where since rho is positive, we restrict this to the correct quadrant. We don't allow the opposite quadrant like in polar coordinates. So it might be the arc tangent, and it might be arc tangent plus pi. If it's on an axis, it's obvious, right? It's the same thing as you did before. And then now phi, what are we going to do with phi? Well, if we drop this perpendicular back to here, parallel to this one. Now I've got a right triangle right here. And since this is rho and this is phi, by trigonometry, this must be rho cosine phi, so that this over this is cosine. And this one must be rho sine phi, so that this over this is sine, right? Opposite over hypotenuse sine. Wait a minute. C. That C, I can solve this for phi by dividing and say, well, z over rho cosine phi. And now we're going to make a restriction. Since we can go all the way around in theta, as far out as we want in rho, to cover every point in space, we only need phi to go from the top axis down to the bottom axis. We don't have to let phi go from 0 to 2 pi. We just let it go from 0 to pi, straight up to straight down. And by rotating down and then taking theta around wherever we want, we can get any direction in space and then just move out a distance rho. So we're going to restrict phi to be between 0 and pi. And in that case, cosine phi equals this is equivalently phi equals arc cosine phi over rho. Now, if you look in textbooks, actually most of the textbooks will emphasize this one. Cosine phi equals this, and then you figure out the angle phi. But in fact, since phi is restricted to be between 0 and pi, this always works. I like to write it that way to emphasize it. So also, the last equation, use compute phi directly, always works as arc cosine c over rho. As long as you're not at the origin, where you get a division by 0. If you're at the origin, then phi is arbitrary. In fact, theta, to identify the origin, you just put rho equals 0 and phi anything, it's still the origin, right? So aside from the origin, you use those equations, and then the origins put rho equals 0. All right, those are equations 1. Given rectangular coordinates, you can put it this way. Technically, to put all rectangular on the right, I should put z over square root x squared plus y squared plus z squared, but this is easier to remember, right? If you've already computed rho up here, then you can. It's given x, y, z, these things, always compute rho, theta, phi. All right. Now we can go the other way. We've already got one of these here. Look, c is equal to rho cosine phi. If I'm given spherical coordinates, I can get z back. So equations 2, I can put z equals rho cosine phi. Now, what else can I do? Well, rho sine phi came from this triangle, but this is out of a big rectangle, so this bottom part here is also rho sine phi, right? Because it's rectangle, 4 right angles. So if this is rho sine phi, now what I can do, let me get a different color here because it's going to be tricky. If I drop a perpendicular here back to the x-axis, right angle, what's the length of this side? Here's the angle theta in the triangle. The hypotenuse of the right triangle is rho sine phi. This side, since it's the opposite side, is always rho, it's always the hypotenuse, rho sine phi, times the sine of the angle. Sine theta. Right, so it's hypotenuse, sine of the angle, opposite. And this side here, again from trigonometry, is the hypotenuse times the cosine of phi. So hypotenuse, rho sine phi, cosine of the adjacent angle, theta. But wait a minute, this is x. This one is y. So there's how you compute x and y. See, let's put these over here too. And really, you have to memorize these. You can figure them out if you need to on the test, but it takes a while. And these come up enough, and you'll see them in later courses. They're used substantially in calculus 4, for instance. In calculus 4, when you want to compute volumes of solids, you do integrals of integrals. And when you're doing these in multi-dimensional space and you have a spherical symmetry, these coordinates are very useful. They make your integrals a whole lot easier. So we'll say that these are worth memorizing. Rho cosine theta sine phi x rho sine theta sine phi for y. Here are the conversion equations back. These are easier. These always work directly. You don't have to say, well, if it's in this quadrant, you do this, and if it's that quadrant, you do that. Also in three-dimensional space, we should point out, instead of quadrants, we have octants, right? Just as in the plane, we divide the axes, divide the plane into 4 quadrants, taking counterclockwise, 1, 2, 3, 4. In three-dimensional space, the coordinate planes, right? Here's the XC plane. Should draw that in green or something, shouldn't I? I'll leave the axes in black. Let's just the axes in black. Then the XY plane, excuse me, the XC plane is this one. YZ plane is this one. The XY plane is this one. And that breaks up three-dimensional space into 8 regions called octants. And you consider above the XY plane, over this XY plane. Looking down on the quadrants that you have for the XY plane, you call those octants with the same number. So where all three coordinates are positive, you call that octant 1. Where when you're over quadrant 2, you call that octant 2. When you're over quadrant 3, you call that octant 3. And when you're over quadrant 4 with X positive and Y negative, you call that octant 4. Then if you're down below the XY plane, looking up, then you just add 4 to each of these. I guess put this. So octant 1. Now below octant 1 is octant 5, where Z is negative and X and Y are positive. Below octant 2 is octant 6. Below 3 is 7. Below 4 is 8. So 8 octants. Okay. All right, so now that we have the conversion equations, we can convert following coordinates. So as I said, convert. Oh, and I also need the following note also. Rho is greater than or equal to 0 by this prescription, since it's the root sum square. This radical sign means a non-negative number that has a square, so it's never negative. Theta is arbitrary. Well, but theta is an element of the real numbers. Can be any real number. You can go around 230 times and it's still considered a legitimate angle. But phi is then restricted to be between 0, pi, 0 and straight angle. Always in these coordinates. After all, it's the arc cosine. All right, now let's convert these. Convert from rectangular to a spherical. And it has the same problem that the cylindrical coordinates do. Every triple that satisfies those three requirements identifies a unique point, but every point actually has an infinite number of ways of describing it, because you can add 2 pi to any theta that you see. So every infinite number of values of theta, all separated by a multiple of 2 pi. And if you're along the positive z-axis here, theta is arbitrary. You just put phi equals 0 to stay on the positive z-axis. Go up a distance rho, and theta doesn't matter. So all thetas are the same. And if you put the negative z-axis, well, that's phi equal pi, and rho equals however far you go. It doesn't matter what theta is. And if you're at the origin, then you just put rho equals 0 on both theta and phi can be anything. So there's those ambiguities in coordinates. You can have an infinite number of coordinates that describe the same point, but once you give a triple, it identifies it. First, from rectangular to spherical, following point, 1 minus square root 3 minus 2. This is the hard way here because you have this arctangent problem. Well, you just say rho by 1. Rho is just directly computed the root sum square. There's 1 squared plus minus square root of 3 squared, 2 squared is the square root of 3, plus 4 is 7, plus 1 is 8, square root 8. Always reduce these, so I'll call that 2 square root 2. Then tangent theta has to be y over x, just like before. It's minus square root 3 over 1 in the correct quadrant. How do I put this in the correct quadrant? I rewrite it as minus square root 3 over 2 over 1/2. And say this must be y and this must be x on the unit circle. Or you could put the top one positive and the bottom one negative. And this could be y and this could be x on the unit circle. Which one do we want? We want the same quadrant as the original point, x positive and y negative. So this time we could have used the arctangent. X1, look at the unit circle, with x positive and y negative is this one. So we throw out that one, that's the wrong quadrant. 4. Wait a minute. Y negative x. And go down to this point. Minus square root 3 over 2, 1/2 on the unit circle. Observe that at that angle, this has to be reference angle of pi over 3 for trigonometry. And this is square root 3 over 2, and this is 1/2, and this is 1. Angle that we want must be, well, we have an infinite number of choices, right? So let's pick it, be between minus pi and pi. We could say the actual angle to this ray here is minus pi over 3. We'll figure that one for theta. And then cosine phi, this is why the books put it as cosine phi equals the numbers for exact calculation. We'll say cosine phi is c over rho, right? Is, let's see, minus 2 over 1. And then you can, on your calculator, calculate phi equals our cosine of that. However, whoops. C over rho. Rho was 2 square root of 2, sorry. C over rho. Minus 2 over t square root of 2 is minus 1 over square root of 2, right? You recognize that one. That's also known as minus square root of 2 over 2. That means that phi must be the arc cosine of that. Negative pi over 4. Only one choice for phi. So I got this one. My coordinates for this point, spherical coordinates. Therefore, 2 square root of 2 minus pi over 3. There's one choice for spherical. What are all spherical coordinates? You just add, since it's not on the z-axis, that's where there's ambiguity. On the z-axis, theta can be anything, and coords and theta and phi can both be anything. All other places, all spherical coordinates, you see add 2k pi to the theta coordinate. 2 square root 2 minus pi over 3 plus any integer multiple of pi over 4. So that'd be all of them. These were 2. Now we can convert the other way. Yeah, 2k pi where k is any integer. I just said it. I should write down. K can be 0, 1, minus 1, 2, minus 2. Yeah, it's a k there. When I write j, k, l, m, n, those will always refer to integers. It's k that time. Okay, let's try converting the other way. Convert spherical coordinates, which are always on the order rho theta phi. Let's see. 5 pi over 6 pi over 4 to rectangular coordinates. Now it's just directly by equations too. There's no doubt in this. By 2. And when you get these angles that are special, you want to compute them exactly. X is equal to rho 5 times cosine theta pi over 6 times sine phi is pi over 4. You just have to go back to the unit circle and figure all these out, right? You've got 2 triangles. The one is the 30, 60, 90 with pi over 3 here, 60, pi over 6 here, 30. Now this side is square root of 3 over 2, and this side is a half, and this side is 1 that fits right in the unit circle. So we say cosine of pi over 6, this one is adjacent over our hypotenuse is square root of 3 over 2. And the other special triangle, of course, is the 45, 45, 90, or pi over 4, pi over 4, pi over 2 angle. This one, you give it side square root 2 over 2, square root 2 over 2 and 1. We say the sine of pi over 4 is opposite over adjacent, is square root 2 over 2. Evidently have 5. The square roots combine, right? That is square root 6. This is what you'll see in the back of the textbook. Similarly, y is rho, first coordinate 5, we're going to 5, sine theta, sine pi over 6, sine b becomes 5 times sine pi over 6 is opposite over hypotenuse is now 1/2. Sine of pi over 2 is again square root 2 over 2. And this time we get 5 square root 2 over 4. And then C just computed directly is rho cosine B, rho cosine pi over 4, theta doesn't appear. Cosine of this angle is adjacent over hypotenuse is square root 2 over 2. So the C is just 5 square root 2 over 2. And there's my coordinates x, y, z. 5 square root of 6 over 4, square root of 2 over 4, and 5 square root of 2 over 2. So going that way is no trouble at all. Just got to remember your trick. So on approximately Monday, I'm going to put out a set of practice problems for the final exam. So be looking for those. But I'll try to remind you Monday night. We'll talk about the final next time, which I think is probably just might as well be by email again because it's still not cleared up for everybody. And a lot of you still haven't got your second shot and so forth. And so we'll just make it by email. We'll talk about that next day. Now we want to be able to convert equations is the other thing. To convert equations, you use either 1 or 2 as is easier, just like we did with polar coordinates. And then there's tricky details because sometimes to get what's in those equations, you have to multiply through by a variable. You have to think about what if that thing is 0, right? We'll say both or either use 1 or 2. And I could give you, for instance, this one. Here's some important things to recognize. What if, let's say, convert to rectangular coordinates and sketch? Partly, it's important just to have an idea what these variables equal constant are, because those are going to be the important cases. In advanced calculus, you want to be able to have simple integration bounds, and that corresponds to when these variables in the coordinate systems are constants. So suppose I gave you this one, the cylindrical coordinates, a cylindrical equation, r equals 3. How do I convert that to rectangular coordinates? Well, what you do is you say it's equivalent to r squared equals 9 by squaring both sides. But what happens when you square both sides of an equation? X equals minus 2. If I square it, it says x squared equals 4. You introduce extra solutions. Right, so this now has the equation, the solution r equals minus 3. But those, just like in polar coordinates, because this is polar coordinates at z, it's the same circle, right, in polar coordinates. So you actually didn't add any points in the plane, you only added new values of r. So this is r squared equals 9, which now in rectangular coordinates is x squared plus y squared equals 9, or 3 squared. It's a circle in the xy plane, but what is it in cylindrical coordinates? What you do is you say, well, z is undetermined. You draw the circle in the xy plane, and then let z be arbitrary. You extrude it, we say, every point perpendicular to the original circle. What you get is a right circular cylinder. R equals 3 in polar coordinates is a circle, but r equals 3 in a cylindrical coordinates is a cylinder. When you, that's why it's called cylindrical coordinates. R equals a constant of the cylinder. R equals -3 isn't allowed because it's cylindrical coordinates. We only allow R to be non-negative. All right, and actually, this doesn't introduce extra solutions here because we can't let R be -3 in cylindrical. All right, so B, suppose I put theta equal a constant. Theta equals 5 pi over 6, for instance. Remember, in polar coordinates, that was the line at angle tangent 5 pi over 6 through the origin, right? But what is it cylindrical? It's just a little trickier here. Because r isn't negative, what you get is this. You say equivalently, this is tangent theta equals tangent 5 pi over 6. But what's tangent 5 pi over 6? You can run to the unit circle again and say, well, there's 5 pi over 6. These are reference angle of pi over 6, 30, 60, 90 triangle. This side is square root 3 over 2. This side is half. And so the tangent is y over x coordinates. Put this on the unit circle here, shouldn't I? The coordinates are minus square root 3 over 2 and plus a half. So the tangent is the quotient of those. Y over x is minus 1 over square root 3. Let's write down minus a half. Sorry, 1/2 over minus square root 3 over 2. Tangent theta. The tangent theta is y over x by the conversion equations. 2, whatever number it was, equals minus 1 over square root 3. Now, multiply by x, you've got y equals minus 1 over square root 3. When you can do these exactly, I don't want you to leave it as tangent 5 pi over 6. Write it as minus 1 over square root 3. So it's this line, except there's a problem. What's wrong? That would have worked in polar coordinates. It's because x can't be negative here. Sorry, x can't be positive. So it's x less than or equal to 0. It's actually a half line in the xy plane instead of a whole line because I think the intuition is actually here better than the equation. We wrote equivalent all the way down here, but we have to be careful. When we did this step, this wasn't equivalent to this one. Tangent theta equals tangent. This number allows theta to be 2 different angles instead of just 5 pi over 6, right? You can also have 11 pi over 6, the directly opposite angle. So this is equivalent, provided you also specify that you're in quadrant 2 instead of quadrant 4. You don't want the angle in quadrant 4, you want this one, 5 pi over 6. Well, if you're in quadrant 2, so now I'll make them equivalent. Then I need in quadrant 2. Then I want x less than or equal to 0, or equivalent. So let's say x less than or equal to 0. We'll force this line to be in quadrant 2. And so that's where it comes from. It's actually a half line in the xy plane. And then I let z be arbitrary. So theta equals an angle is actually a half plane. In the XY plane, I go out to this angle, 5 pi over 6. Leaving a little reference angle here, pi over 6. In the XY plane, don't think of this as in the board, it's in the XY plane here. And then you can go arbitrarily far out in R, and you can go arbitrarily far up in Z, and so you get this half plane. And so it keeps on going out forever in this direction, but it stops at the axis here. I'll draw a solid line. Ideally, you'd like to draw these dotted. Nobody ever does because it takes too much time. That's the idea. These directions, it extends forever, goes down forever too, but just put it down just to show it. It's that half plane. Out at the end. So R equals a constant is a cylinder. Theta equals a constant is a half plane at the given angle. And then Z equals constant, you already know for rectangular coordinates, that's a horizontal plane. So those kinds of figures are real simple in cylindrical coordinates. All right. So this is a cylindrical coordinates here again also. It's very important actually. Interestingly, suppose I put in spherical coordinates, theta equals 5 pi over 6. Now, well, it's the same thing. Let's just say cylindrical or spherical because it's the same theta. Let's try this one now. R equals 4 sine theta. What could that be? Remember how we did these before in polar coordinates? You do the same thing as in polar coordinates. You try and get the equations that are in your conversion here. There's not a, I can convert R directly, but then I can't convert sine theta directly. So if I multiply through by R, I get R squared equals 4R sine theta. Then I can use the first equation to write R squared as X squared plus Y squared. And R sine theta, using the second set of equations, is Y. And I observe by completing the square as in polar coordinates. Then I get a circle. So here's what I do by subtracting 4y over. Now I complete the square by taking 1/2 of this number squared is 4, and I have to add that to the other side to keep the same solution set. Now I can rewrite this in the standard circle form. X squared plus y minus 2 squared equals 4, or 2 squared. There I know it's a circle in the XY plane, but once again, Z is arbitrary, so it's a cylinder. And this is in cylindrical coordinates. So if I put this as the circle in the XY plane of y equals 2, I go 1, 2. Draw on the XY plane circle. And how do you draw a circle or it look like it's tilted? Remember, if you tilt a circle, it looks to the eye, ignoring perspective, like an ellipse. So you sketch a little ellipse here, and then it looks like a tilted circle. 1, 2, 3, 4. There's the circle in the XY plane, but now you let Z be arbitrary, and it gives you this cylinder. So there's some important equations. We can do some more here. Suppose I want to sketch R squared cosine 2 theta. How about that one? We can put something more exotic that involves all 3 variables, and we want to be able to convert those too. You just use whatever simple, and again, you try and get the things that are in the equation. So if you see a cosine theta, you want to change it to arc cosine theta, that kind of thing. You see want to get a tangent theta or an arc cosine theta or an sine theta in there. Cosine 2 theta, that's not even in the equation. So what can I do? I use the double angle theorem and I rewrite it as cosine squared minus sine squared. Otherwise, I'm just not going to be able to convert it. So use the double angle identity to convert it. Now I notice by multiplying out, I can get an arc cosine theta quantity squared and our sine theta quantity squared. There we go. Now I can convert it to using the equations I know. Z is Z in cylindrical coordinates. So these are cylindrical coordinates converted to rectangular. This just becomes x squared minus y squared equals. What is that? This is a tricky one. Write it in the reverse order, maybe it'll look better. Z equals x squared minus y squared. So we're from last time. Rewrite this as x squared over 1 squared minus y squared over 1 squared more suggestively, and it is a hyperbolic paraboloid, right? Z equals x squared over a squared minus y squared over b squared. Hyperbolic paraboloid. So most of these, the way to sketch them is to convert them to rectangular coordinates because that's how we're familiar seeing standard equations. We don't have standard equations for these in cylindrical coordinates, right? So we'll convert them to rectangle. Then we'll recognize this as a hyperbolic paraboloid or circle or something. All right. And remember, if Z is on the left, and this is sitting down on the saddle, Z equals x squared, you go up on the xz plane. And Z equals minus y squared, you go down on the yz plane. So the saddle looks like this. I don't know the origin. Saddle's oriented that way. And you do some traces. All right, there's converting some cylindrical equations. Hard there. Just try and get the things that you see in the equations as well. How about we convert some spherical coordinates? Suppose I had rho equals 2 secant phi. Spherical coordinates. How do I convert that to rectangular? Well, once again, I want to get the things that are in the equation. I don't have secant phi in there. What do I have? I have sine phi and cosine phi, and they all have to be multiplied by rho. So what I might do is multiply both sides by cosine and rewrite this as rho cosine phi equals 2. Right? Provided cosine phi isn't equal to 0, I wrote equivalent, but I multiply both sides. I can multiply by any non-zero number. Where cosine phi is 0, this fails. So we'll say actually technically cosine phi can't be equal to 0, or it's not a solution. Now they're equivalent. But what is rho cosine phi? Oh, I remember that C, and C equals 2. Where we restrict cosine phi not equal to 0. Well, that means phi is not equal to plus or minus pi over 2. Phi can only go between 0 and pi. It's not equal to pi over 2. Phi can only go from 0 to pi. So it is the horizontal plane Z equals 2. Except there's one point taken out, is the function. At this one point right here. That's at Z equals, B equals, oops, no, I'm sorry, that's not. Don't omit that. Phi equals pi over 2 is the XY plane, right? You turn down to here and then you let theta be arbitrary and rho go arbitrarily far out. That's the XY plane. So this is nothing. We can drop this now because there aren't any points in the z equals 2 plane at an angle of pi over 2. Pi over 2 does not. So here's the equivalent equation in rectangular coordinates. It's z equals 2. Now these spherical coordinates, when you have a spherical coordinate equal a constant or immense value, suppose I put rho equal 2, for instance. What is that? Intuitively, you can get it right away because rho is the set of all points. I'd say rho is the distance from the origin to the point. So this is the set of all points at a distance 2 from the origin. It's the sphere of radius 2. That's all it is. So we draw it by drawing a circle in the YZ plane and beginning it. Going out to 2 here and 2 here. That's what it is. It's a sphere. If you want to convert it by equations, how do you do it? Oh, well, this is square root x squared plus y squared plus z squared by using those spherical equations. Equals 2. That's fine, but the more conventional way in rectangular coordinates is to now square both sides and say x squared plus y squared plus z squared equals 2 squared. The standard equation for a sphere. Remember we did spheres a while back. X minus x0 squared plus y minus y0 squared plus z minus z0 squared equals r squared is a sphere of radius r at x0, y0, z0. So this is a sphere at the origin of radius 2. Right? And there it is. Right? So this converts the equations. This is what we knew intuitively anyway. You want to be able to do it. This is an important one. It comes up. What if I put phi equal pi over 6? I wonder what that looks like. If you put phi below a constant, you can think intuitively. This is the intuition part that you should know. You can come down from the z-axis at an angle of 30 degrees, pi over 6, right? And then theta can go all the way around. Right? And then rho can go arbitrarily far out. So this thing extends actually up to infinity, but it's a half cone. That's how to figure it out intuitively. Just imagine drawing down a pi over 6 with any angle at any distance. That one. Times cap. All right, so now the actual conversion equation, if I want to convert it directly from here, right? I don't have in those equations phi. What I have is things like cosine phi. So I can take the cosine for the sine. Let's say cosine of phi equals cosine pi over 6. Cosine pi over 6 I know already is square root 3 over 2. And cosine phi, z, rho cosine phi is z. So now I need to in order to get it in the usual form, I can write this as rho cosine phi equals rho times pi over 6, which is square root of 3 over 2. And now, how do I convert that? Well, rho cosine phi, recall, is z. Rho is the square root of x squared plus y squared plus z squared. And now I can figure out what this looks like by squaring both sides. I get z squared equals x squared plus y squared plus z squared times Coords. So now I can subtract over and get z squared times a fourth equals x squared plus y squared Consequently, z squared equals 4 x squared plus 4y squared. And now you start to see the equation of the cone coming out. This is z squared equals x squared over a half squared plus y squared over a half squared. That was the standard equation for a cone. X squared over a squared plus y squared over b squared equals z squared is a cone. Oh, but there's something missing. These weren't all equivalent statements. What did I mess up? Right here, when I squared both sides, I can introduce extra solutions. This allows z to be negative, where this means the non-negative square root. So I have to attach here z greater than or equal to 0 to make it equivalent. So now these all be equivalent. Get tired of doing all the details, but they really are important when you get the whole code, right? All right. So same thing, carry it down. Z greater than or equal to 0. It's a half cone. So there's the derivation by equation. It's kind of tricky, but you try and put it into rho cosine phi. When you see a square root, you square it, and you can. We can do one more. Taking too long in this section. All right, let's take suppose I gave rho minus 2 sine phi cosine theta equals 0. What's that? This looks kind of familiar, right? Cosine theta sine phi is almost what we had for x. I just need a rho here, so I multiply it through by rho, and that's going to introduce the origin as a solution, so I have to check that later. Rho squared minus 2 rho sine phi cosine theta equals 0. Now I can convert it. Now I have rho sine phi sine theta. This is just x. And so I have rho squared is x squared plus y squared plus z squared by the conversion equation. Minus 2x equals 0. And what I'm going to get out of this? Well, I complete the square. X squared minus 2x plus y squared plus z squared equals 0. Rearranging the terms. I complete the square by adding 1 here, then I have to add 1 to the other side to balance the equation. And now it's x minus 1 squared plus y squared plus z squared equals 1 squared. It's a sphere at 1, 0, 0 radius 1, according to the standard equation for a sphere. X minus x 0 squared plus y minus y 0 squared plus z minus z 0 squared equals r squared. Sphere, radius 1 at 1, 0, 0. So what I do is I just have a sphere here that's sitting up on top of the xy plane, right on top of the origin there of radius 1. Oops, except I drew it not there, x direction. Drew it in the wrong spot. 1 unit out the x-axis. There's the center. Got 1, 0, 0 right here. Equator here. Circle radius 1 here. There's the sphere of radius 1 at 1, 0, 0. Just touches the origin. All right, that's all we need to do on those and be able to convert them. So it leads to a lot of interesting pictures you can draw. And you can see some of these things come out with reasonable equations and these other coordinate systems. All right, the rest of tonight, I want to talk about vector valued functions and calculus figure out. And you see one of the reasons we didn't have a third test. One of them is it takes too long to grade the test, but the actual bigger factor was that this semester, I know we have a terrible time just finishing this next few sections on vector valued functions. If I would have had one more test, we'd be out of time after this week. Vector valued functions, one day a review and one day to take the test, right? What is a vector valued function? Well, what is a function? Remember, a function in calculus 1 is a rule. If each input assigns exactly one output. So you put in an x and get out a y. Here, if it's a vector valued function, you put in an element of a set and get out a vector. So for us, we're going to put in numbers, and we say these are functions, let's say. F t equals x of t I plus y of t j. Or instead of F, we might use the letter R. This is what physicists like to use. They call R the position vector. And you can do this in the plane. You put in a number t and get out a vector in the plane, or in free space or higher dimensions. We can say R of t is just an ordinary function, sometimes called a scalar function, to identify it as not being a vector. X of t I plus y of t j plus c of t k. So this is how you can specify a rule. If you input t, a real number, get out a vector. The sketch of a vector valued function with some domain a less than or equal to t less than or equal to b is the point at the terminal point of x of R of t. So we go back to parametric equations. X of t, y of t, and we just plot the endpoints. And so the idea is want to sketch, for instance, R of t equal 2 cosine t I plus 2 sine t j. What is that? These are the points with coordinates. Two cosine t, 2 sine t, which we recall is a way of parameterizing a circle, right? This is, if you put cosine t, sine t, you get the unit circle, right? Each point would be a point on the unit circle at polar angle t. If we take 2 times each, it's just the circle of radius 2. And so what we get here, circle of radius 2, take any polar angle t, for theta, go to the point not cosine t, sine t like you would on the unit circle, you get to the point that's twice as far out, 2 cosine t, 2 sine t. And so the idea is this vector sweeps around and its terminal point sweeps out the circle of radius 2. We can, in this case, restrict this, since it will do the circle over and over, and say, well, let's restrict t between, be between 0 and 2 pi, so it only sweeps out the circle once. So that's a vector valued function. There are other curves that are useful besides circles. For instance, suppose I did this one. Sketch R of t equal 2 sine t I plus cosine tj. What kind of curve that is? Well, what you do is you again realize that this is the x coordinates as a function of t, and this is the y coordinates as a function of t. And you try to eliminate the parameter like we've done before. How can I eliminate the parameter there? If I take x over 2, that's the sine, right? X is 2 sine, so x over 2 sine. If I square that and add it to y squared, which is y is cosine, I'll get sine squared plus cosine squared. 1. So evidently, these points are all on x over 2 squared plus y squared, x squared over 2 squared. Let's write it that way. Well, plus y squared over 1 squared equals 1, which is what? It's an ellipse in the plane, right? X squared over a squared plus y squared over b squared equals 1. So these are parametric equations for ellipse. And actually what you do to get between, we can make the following note. If you put x equals a cosine t, and y, let's put it this way. R of t equals a cosine ti plus b sine tj is always an ellipse. X squared over a squared plus y squared over b squared equals. All you do instead of putting a and a to get a circle of radius a, you put a and b, now you get an ellipse instead of a circle. A circle in special case would be equals a. And then, wait a minute, this one I use sine and cosine in the reverse order. What's going on? Well, you can observe that if you interchange sine and cosine, it actually runs over the same ellipse. It just does it starting at a different angle. This one, when you put t equals 0, it's pointing with x0 and y equal 2. So it starts up here, and as t increases, sine and cosine become positive, so it goes around the ellipse this direction, starting at 2. Or if you read this prescription with x equal cosine, then it starts at the angle 0. Starts on the x-axis and moves around this way. So sometimes we like to put arrows on these to show the direction in which it's traversed. Although some cases it'll go back and forth. But these are always ellipses. A sine and b, a cosine and b sine always gives you an ellipse, no matter which coordinates you put them on. One of sine, one of a sine, and one of b. And some of these others, it's very easy. For instance, if I put r of t equal 2 minus 3t I plus 1 plus t j, what does this sweep out? Just think that this is x of t I plus y of t j. And this is the prescription we gave previously for lines. If x equals at plus b, y equals ct plus, that was always a line. This is equivalently the parametric equations. X equals minus 3t plus 2, y equals 1t plus 1. It's a line, and whenever it's linear equations like that. You can find out what the line is simply by solving for y as a function of x, right? So in this one, you say, well, this means that t equals y minus 1, and then I can plug it into the other equation. Plug it into this one. X equals minus 3t plus 2. Put in y minus 1 here. Evidently, x equals minus 3y plus 3 plus 2. X equals minus 3y plus 5. And so you can solve for t in one equation, put it into the other one, and figure out what the equation is. Evidently, y equals x minus 5 over minus 3. Y equals minus a third x plus 5/3 is mx plus b form. And then you sketch it. So those are parametric equations. The important cases are the circles and the lines. Whenever you see AT plus B and CT plus D, recognize it sweeps out a line. You can always do this. Whenever you see a sine and cosine each times the same number, it's a circle. But if you see sine and cosine times different numbers, then it's an ellipse with those semi-axes that multiply the sine and cosine. All right, I guess I've got to stop and I'm out of time. Let me give you these. I wish I could have finished this section a little more, but I think you can still do most of the problems. Next time, what we'll do is the calculus of these vector valued functions. What we're going to do is generalize calculus in the plane, be able to do more exotic curves, arc length of that kind of thing. Let's see. Spherical coordinates. So in cylindrical and spherical coordinates, look at 11.8. 1 to 17 odd. And 19 to 43 every other odd. Very similar to what we did today. Any questions that you have, sometimes I can do better explaining this if you ask me a few questions. And then 12.1 is just simple introduction to vector valued functions. Put in a number T, get out a vector. Let's look at 5 to 29 odd. A couple more of those I do next time. And then next time we'll do calculus for these things. Maybe I should mention in that regard, if R of T is given as a secant T plus I B tangent T, if you secant tangent in either order, this actually comes out to be a hyperbola because this squared plus 1 equals this squared. You can use a similar thing. I don't have time to do that today. Or instead of this, you can use hyperbolic sine or hyperbolic cosine. And this also comes out to be a hyperbola. So there's a couple other curves we haven't discussed yet. All right, thank you, everybody. Sorry to run over a bit.